Good morning. My name is Daniel Verkamp. I'm a software engineer at Intel, and I'm one of the SPDK maintainers. I'm going to be talking about the logical volumes layer and its slices and dices. So let's get into it. You can read that real quick. So we're going to talk about basically what logical volumes do, which should be pretty familiar, but just a basic overview to make sure we're all on the same page. One way that you can use it to give us sort of a motivating example. And then we'll dig into some more of how it's actually used from the API point of view as a user, and then under the hood a little bit about how it works based on the blobstore. Okay, so if you're familiar with Linux LVM or other logical volume management type of layers, this is very similar. But basically, you can take a large block device and slice it up into many smaller pieces, which are exposed as virtual block devices. So if you remember Paul's talk from yesterday, this fits right into that virtual block dev layer. You can manage the volumes independently, so you can create volumes on the fly while other volumes are in use. You can delete, resize at runtime. So the comparison here is to something like the GPT block device, which we had before, which just reads a partition table at startup, but it's static and you can't change it while it's running. So the most recent changes we've made here in 1804, we now support thin provisioning, snapshots, and clones. So we're going to get into a lot more detail about how those work in a minute, but basically you can take a snapshot of a volume at any time and then clone it into a read-write volume. And as I said, it's implemented as a virtual BDEV. So it fits into all of the SPDK applications that use BDEVs. So the vhost target, NVMe over fabrics, all those sorts of things. So here's this motivating example. Let's say we want to operate a VM hosting service, and we've got one large SSD, but we don't want to give that whole SSD to a single VM. We want to slice it up into small pieces, and we want to do that dynamically. So let's say a new user shows up and wants a new VM and wants 10 gigs of storage. We want to be able to do that without shutting the whole system down, without interrupting the service of those other VMs. And that's the basic operations you can do, right? Create new volumes, delete volumes, and resize them. All right, so this one's going to be, imagine the color of the volume here is the current state. So it starts out as orange, which looks yellow on the screen. We take a snapshot of that, which is, imagine it as a copy. It's not really copying the data, but it is effectively a copy of the data that's a read-only state of that volume at that point in time. So then we do some more writes to the volume. It becomes green, so it's a different state just to show that we wrote something to it. Our snapshot is still orange, right? It's the original state. We can make a new snapshot. Now it's the new state, and we have both of those snapshots available. We do some more writes. Now it's blue. We get a blue snapshot. We do some more writes, a different shade of blue. Okay, so now let's say we like that last snapshot. We want to make that into our base image for that VM hosting service. Maybe we installed Debian on it or something like that. Now we can make a clone of that, which is a read-write copy of a snapshot. And we can make another clone. So you can make as many clones as you like from a snapshot. And now those are essentially independent copies that you can write to. So now we're writing to those clones, and it's not affecting the underlying snapshot. Now, like I said, these are effectively copies, but they're not really doing a copy under the hood. And we'll talk about how that works later. But it's basically copy on write of just the clusters that you write to. So you're not paying for data that's copied here as long as it's not actually modified. All right, so this is how the API looks from the point of view of the JSON RPC interface. So you can use this through the rpc.py script that we have, or SPDK CLI, which Jim showed yesterday in the state of the project. And basically, you can construct a volume store on any BDEV. You can create volumes on that logical volume store, and then you can snapshot and clone. You can, of course, consume these through the rpc.py script or the other script directly, or you can actually connect to our JSON RPC interface if you don't like Python or you have your own management tool. And the JSON RPC interface is meant to be a stable API, so you can program directly to that, and in the future releases, it'll continue to work. All right, so if you're here last year, Ben Walker gave a talk about how the SPDK blobstore works. I'm not going to go into deep detail about this, but basically the logical volume store is built right on top of the blobstore. And the blobstore gives us, the main thing that gives us is block allocation. So we take a disk, we chunk it up into what we call clusters, which is the allocation unit, and we give those clusters to logical volumes. That's basically all that we need from blobstore. So here's that cluster-based allocation. So for logical volume store, the default cluster size is 4 megabytes. That's the unit of allocation. So you can have any multiple of 4 megabytes you like as your volume size. And it takes clusters from anywhere on the disks that are free. So this does mean that you get potentially fragmentation in the sense that clusters are scattered around the disk, but they're fairly large. So as long as your IOs are mostly within clusters, which will be the common case because they're 4 megabytes, you get fairly sequential access on the actual underlying BDEV. So as it says here, no external or internal fragmentation in the allocation sense, right? So everything is allocated in multiples of 4 megabytes, so you can never have wasted space inside a cluster, just because we always allocate them in fixed size chunks. So if you call, ask the logical volume store, how much free space do you have, and it tells you 128 megabytes, you can allocate exactly 128 megabytes of space in any multiple of 4 meg you like. It's never going to lie to you and say that you have more space available. All right, so now we get to the new stuff. So this 1801 had the basic logical volumes functionality. These thin provisioning and snapshot and clone are new in 1804. So you can use this today, but it's fairly fresh. The basic idea here is that now instead of allocating all the clusters for a logical volume up front, you can say, make this a thin provision logical volume, which means that all of the clusters will be unallocated until you actually write to them. So how this works under the hood is actually, we have a layering functionality in the logical volume store. So you can imagine that there's a block device, which is not really there, but is essentially returning zeros for all reads. And then we layer our new thin provision volume on top of it. So if you read one of these unallocated clusters, it sees that that cluster is not really there, and it reads down the next layer. So imagine you're looking down from the top, and you can see through to the zeros. So now if we write one of these clusters, now you can't see through that cluster. So that means that you have the real data stored there. And this means that you don't allocate the clusters until you actually write to them. So if you have a disk that's mostly empty, in fact, like the VM hosting case, you can save a lot of space on the disk, and you don't need to allocate all the clusters that are just filled with zeros. So that's thin provisioning. So now let's step to the next. Snapshot and clone works in a very similar way, except now we're layering a snapshot underneath a new clone, which is a read-write logical volume. So we start out in the same way. All of the clone clusters are actually unallocated, which means you can read through to the snapshot, which is read-only. But then if you need to do a write to one of these clusters, the process behind the scenes is actually that we read the cluster from the snapshot, allocate a new cluster for the clone and fill it in with that cluster, and then perform the write that the user wanted to do. So again here, you're sharing all the clusters of the snapshot with as many clones as you have, as long as you don't write to those clusters. Basic copy and write functionality. All right, so that's sort of the basic functionality that we have. Let's talk through a few of these things that fit into the virtual block device layer that Paul talked about yesterday. The basic idea here is that you can allocate a single BDEV into smaller pieces. But what if you have more than one SSD? You can't span a logical volume across multiple BDEVs today. So we have work outstanding. As Jim said in the talk yesterday, we have actually 2 separate implementations of this coming down the pike. And we're going to take the best out of those 2 and combine them into some kind of spanning or RAID type of virtual block device. So that will mean that you can layer the spanning block device on many SSDs, and then a logical volume store on top of that. So that will give you even more functionality in terms of slicing up a large pool of storage into smaller pieces. Another problem or potential pitfall here is that the data is actually unencrypted on the disk. Now this is not specific to logical volumes, but if you're running, for example, the vhost VM hosting use case, you probably want to be able to delete an image for a particular user without writing zeros to the whole disk for that user. So we have a work-in-progress encryption virtual block device module, so you can actually encrypt each particular volume with a different key. And then if that user goes away, you can just throw away the key for that particular module, or that volume, and then it won't be readable anymore. So we do have the copy run write facility, which helps you save a lot of space on the disk. if you're doing these particular cases where you start with a snapshot and make clones. But there's other potential for data reduction. So if you have a lot of disks that are storing very similar data, there's a lot of cases where you'd want something like compression or deduplication, and that's not built into the logical volume store. But again, we can layer this on top of another virtual block device that provides those deduplication or compression functionality. Another problem here is that we are allocating space, so we're evenly provisioning the space to the users, but the underlying SSD has a limited amount of resources in terms of bandwidth and IOPS as well. So logical volume store doesn't provide any additional guarantees about fairness there, but we do have a feature for that as well, which is the block device QoS support, and Gong's going to talk about that next, actually. So you can configure different IOPS limits for each BDEV, for example, for each volume. And maybe even if you're doing a VM hosting use case, you might want to say certain classes of users pay more and they get a higher IOPS limit, things like that. Additionally, right now, we have that resize functionality, which will let you shrink or expand a disk. And it does, under the hood, work in terms of resizing volumes while they're open, and we don't have any like thread safety bugs or anything there. But there's no way for right now for the next layer up to know that their underlying block device changed size. So we have plans to add notifications, just a hook, so that the next layer up can send a notification to vhost SCSI or whichever protocol is talking at the top to let it know that it resized. So right now, that's actually prevented in code just to make sure that your guest VM or other user of that module, that volume doesn't get confused. But that's definitely a potential place for improvements. And I think I zipped through this pretty quick. So we have lots of time for questions. So please ask away, and I can go back and explain some more detail, some of these diagrams if that's interesting. I got a question here.
Hello.
Hi.
So, as I see, there's a lot of functionality which is overlapping with the LVM project in the Linux, which is also open source. So I'm just wondering, is it possible to collaborate with them so that I think there's a duplicated effort going on both sides, right? So maybe some of your work they can benefit and their work you can benefit. Just
Sorry,
curious question.
Could you repeat which project?
LVM.
LVM, yeah. So yeah, this is a different implementation under the hood than Linux LVM. It's similar, but LVM that's implemented in the Linux kernel actually has a lot more functionality. So it has built-in support for spanning and that sort of thing, and it uses a different on-disk format. So in theory we could, but one of the main issues is that LVM is GPL licensed and we're BSD licensed, so we can't necessarily share code. But it's a good question. We want to perform any of the provide any of the features that they provide if they're interesting, but we probably can't share the implementation.
Daniel, we got a couple of questions over here.
Go for it.
Hey, one is the age-old question of how do you report capacities once you have snapshots in a volume? So for example, if you had 1 gigabyte to start with and the user takes a snapshot, do you still allow the user to consume up to a full gigabyte for his new writes on the original volume? Or do you blow away the snapshot, or do you fail the I/O?
Yeah, so I guess, back to the original thin provisioning slide, even disregarding snapshots for a second. As soon as you have thin provisioning, now you can over-provision the disk, right? So you can say, when I create a volume, I want this to be 10 gigabytes, but I don't actually allocate 10 gigabytes worth of clusters. And I can do that many times, and in theory have larger virtual volume size than I actually have physical space on the disk. So if you write to a cluster and there's no free clusters at that point, there will be a space type of error return back up to the next layer. So it's definitely possible with thin provisioning as well as snapshots, right, where you can over-provision the disk and run out of clusters at runtime. So right, you can either make sure that you always have plenty of space on the disk before you create new snapshots with thin provision volumes, or just let your guest VMs deal with that, right? Because that's an existing error that you can get back from even base NVMe SSDs, right? Because NVMe spec provides thin provisioning.
Right, but the case referring to it is where the parent was not thin allocated, it was fully allocated. Then you took a snapshot, and now you have to make a choice. when you run out of space, what to do. And I was just curious, people have taken different approaches, and what did you decide?
Yeah, I'm not sure if I totally understood the question, but right, when you create a snapshot, it's not actually copying anything at that point except the metadata, right? So we've got a cluster map which just points at which clusters are in a logical volume. So you need to make a new one of those for the clone, or for the snapshot. But the underlying clusters are all shared until you write to them, right? So at the point that you write to a new cluster that needs to be allocated, that's when you need to either have a cluster available or return a no space error. Does that make sense?
All right, second question. Mentioned metadata. How and where do you store it? How do you manage its transactional attributes? Any thoughts on that?
Yeah, so the metadata, which is which logical volumes exist and where they are on the disk, is all carefully designed so that it can be written with the guarantee of NVMe SSDs, which is 4K blocks at least, are atomic, right? You can write a 4K block, and it's always either fully written or not written. So the metadata is designed to take advantage of that. The data itself is not, does not provide any transactional guarantees, just the same base guarantees that the disk gives you, right? So that's up to the next layer up, right, in your guest VM or whichever software is writing to the disk to make sure that they're performing flushes or doing transactions. But the metadata is power fail and crash safe. So you'll either get some fixed point in time if you crash or don't write all the disks, write all the metadata.
Hey, I have two questions and we'll combine it in one in the interest of time. So your cluster size is 4 meg.
By default, yeah.
What happens when you snapshot and then you just write 4K to a new cluster?
Yeah.
Do you have to remodify write? And what are the performance implications of that?
Yeah.
Especially when you have large chains.
That's a very good point. So that I forgot to mention in the part about cluster size, there's trade-offs, right? So the larger you make the cluster, the less metadata overhead you have, right? And the less likely it is that you're going to cross a cluster boundary. But when you do one of these copy and write allocations, you have to copy a full cluster into that new cluster. So if you have a 4 megabyte cluster, that means a 4K write might turn into a 4 megabyte read followed by a 4K write. So after that point, then that cluster is allocated and it's fast again, but you will take a performance hit for that first write. It doesn't matter how long the chains of snapshots are because you're always going to read one cluster worth, but the cluster size is very important. That's a trade-off you're making when you choose the cluster size.
So if you have a large chain and you didn't write to, it's a cluster-based chain, not a volume-based chain.
Yeah, right.
Okay.
So all of the snapshots below you are all read-only, and none of those clusters get allocated if they're not already allocated because they can always read through to the one below them. But that final clone on the top that's writable will get a new cluster and then read the whole cluster. So initially we had actually logical volume store allocating 1 gigabyte clusters, which is fine when you're not doing thin provisioning. But yeah, reading a whole gigabyte for a 4 kilobyte write is not really very good, right? So 4 megabytes is a good trade-off point, right? Where you have small enough metadata overhead, but not too much data to copy when you need to do a cluster copy and write.
Question on your left? All right. It seems like a lot of the limitations can be solved with BDEV modules. Is there, can you stack a lot of these virtual BDEVs on top of each other? And if so, is there like a hard or soft limit on doing that?
Yeah, so you definitely stack modules. That's kind of the intent, right? You can, a virtual BDEV module is just one that consumes BDEVs at the bottom and exports BDEVs out the top. So as you can imagine, you could take logical volumes and stack that on top of encryption or vice versa. You can do as many as you want. That's not limited by anything except, if you run out of RAM, right? So, again, additionally, you're going to allocate a new BDEV IO at each level there. So there is some small performance impact to layering, but there's no inherent hard limit to how many you can stack. I think I saw one over here. Yeah, I'll go for it.
I'll wave off. I had the same question.
Okay, great.
We got a couple over here.
Yep.
The encryption layer, is that using AES XTS?
Yeah, I'll defer to Paul on that one, but I believe it's using the DPDK crypto framework. So it has support for the Intel QAT and for software encryption, and I believe it is XTS. But I'm not 100%.
No, it's CBC, right?
Oh, okay.
It's on the roadmap, so it'll be in there.
Yeah, Jim's in the back saying that we don't have XTS yet in DPDK.
Your size of your byte grow won't be the same as your plain text and your ciphertext will differ in length.
Yeah, so I was just going to just add what everybody kind of already said this, but yeah, AES CBC is what we support now because it's in the DPDK framework. They have XTS on their roadmap, so we'll deal with that when it comes. The other thing that will be part of the initial release of our crypto VBDev is the Intel Quick Assist, Technologies for Hardware Assist. And it also has, I think, a dozen different ciphers it supports. The software module that's in there initially also supports more than AES CBC. That's just all that we've tested so far. So there'll probably be, a dozen different ciphers per pulled mode driver that come out of DPDK when this thing lands.
Wanted to drill down a little bit. I think you explained the read modify write aspect of it. So the cluster, when it's written to and it gets populated in the snapshot, what happens if the application is doing reads? None of that happens, right?
Right, exactly. Yeah, so let me go back to that slide real quick. But yeah, basically, because the snapshot is read-only, you can always read down to the snapshot cluster underneath you, and it's never changing. So as long as you haven't written that upper-level cluster, you can read straight through, and it doesn't allocate the cluster.
Okay, but a single 4 kilobyte write is going to populate the entire 4 MB.
Right, yeah, and in fact, we have thread safety in case that you have 2 or more threads all trying to write to the same cluster at once even. So you can imagine 2 different 4 kilobyte regions within a cluster are both trying to be written by different threads. Both of those threads are going to see that the cluster is unallocated, go off and allocate a cluster and do all this copying up. But then at the end, they'll race to see which one gets to insert the cluster into the map. And that's done in a thread-safe way with a compare and exchange. So one of them will win, and the other one will just retry its write on top of that. So that's all handled. But yeah, basically, any write to a cluster means that you need to allocate space for that. And since we only allocate space in cluster granularities, you have to allocate and read the whole cluster.
Any other questions for Daniel? Oh, we got
There's one up front here.
We got 2.
And one here.
Hey Daniel,
Yeah.
Can you expand more on the use case of volume running out of space and how the error recovery happens?
Running out of space?
Yeah.
Yeah, so right, when you create these thin provisioned or snapshot clone type volumes, they don't have all the clusters allocated up front, right? And you have a limited number of clusters on the disk. So if you create a whole bunch of these, you can end up in the case where you virtually have exposed volumes that say my size is larger than the underlying volume, right? So now, as you get to this case where you write to a cluster and you need to allocate a new one and bring up the data from the bottom, you can say, oh, there's no free clusters, right? And at that point, we're stuck, right? We can't do anything about that except report the error back up to the next layer. So if you've got VMs that are using these via vhost SCSI, they're going to get a SCSI response code back that says no space left on the device. And they have to deal with that. So if you don't want to get into that situation, that's up to your management code to make sure you don't over-allocate, right? You need to be able to free enough space up to have free space for all the clusters you've allocated.
When you have 2 people collide on a block, the way you described, do you have, on a cluster, the way you described, do you have per block metadata, like a bit that says the block's dirty or the block is clean?
No, so, right, we don't have any per block metadata, it's all per cluster, right? And the only metadata per cluster is the index on the disk, right? That's like 64 bytes pointing at which cluster.
So when you resolve that collision and the guy who tries to insert last redrives their I/O, they potentially regress blocks that they didn't write. It's as if they actively wrote zeros.
Yeah, well, so, yeah, the basic guarantee we provide is the same as the underlying disk. So if you have 2 threads that are writing to the exact same block or overlapping, you get undefined behavior, right? Some mix of those 2. So now this is the same. If you're writing to different blocks, it's fine because they won't overlap, and the cluster will have either the old data from the snapshot or the new data that you rewrote on top. Yeah, but if you overlap it all, then you're in trouble, right?
My point is, when that first cluster comes in, let's assume that the first guy wrote the first 10 blocks.
Right.
And the next guy wrote the next 10 blocks. There's actually not, at a block level, a collision. But at a cluster level, there's a collision.
Right.
So after the first guy writes and then the second guy writes, there's going to be zeros, I guess, in the first 10 blocks. Because you have no way of merging the
Well, it won't need to get
clusters.
merged, except that both of the writes will get submitted to the underlying storage. So let's say you did that, let's say the first 10 blocks got written first. So once you've gotten to that point, the cluster's already allocated, and you've written those 10 blocks to the disk. Then the next guy will come in and write his 10 blocks, right?
So the failure resolution is to drop the cluster that I got allocated. Give it back.
Exactly, yeah, because
Okay,
the first
great.
step is read the original data from the snapshot, which is all read-only. So both readers will get the same data, and then insert into the cluster map. So if any of them that win is fine, right? They're all inserting a cluster with the same data. Just the losers will have to throw away their cluster and put it back in the free map. That's all that happens, right? So it's a good point, and we considered it when we wrote it. So it's all more or less should work.
So just one minor point, going back to some of the questions around what happens in failure scenarios and running out of space. And the virtual block device and stacking that was mentioned earlier. There's nothing that says in the design that you have to actually have a physical SSD below the logical volume. It could be the NVMe over Fabrics initiator, and
Right.
you're disaggregating your storage so that you can continue to grow it, right?
Yeah, and in fact, the demo that we have out in the lobby that John and Vishal are running is logical volumes on local disk and then logical volumes on an NVMe over Fabrics initiator. So, as I said, that vhost or the VM example is just an example. You can use this in any of the applications anywhere that BDevs plug in.
Any other questions?
Cool.
All right, thanks, Daniel.
Thank you.